give better micros and from photothermal spectroscopy corporations, and he will make presentations titles. There's identifying the sub 10 microns unknown organic fluorines metals by laser-based optical detections of infrared photo-induced localized Mirage effect. Okay.
Thank you for the introduction. Sorry, a little bit long title. Change of gear a little bit from previous talk. Thank you for the opportunity to speak here. I'm Michael from Photothermal. All right, so then I'm sure every day maybe you run into something like this. You have a particle that's kind of small, less than 10 microns. If you're trying to analyze a particle like that with FTIR, well, chances are you probably won't get any result out of it. And to a certain extent, it's also true that when you have some contamination on the metals substrate like that along the rim, it might be actually challenging to find out what it is using reflection or FTIR. In the past few decades, this is fairly a repeating theme of its own. But like in recent times, things have changed a little bit, and I want to share that how we can actually go about analyzing these small contamination using infrared spectroscopy. But I do have to go through a little bit about how it actually works. So first, I'll tell you a little bit of background about infrared spectroscopy to begin with, and then follow that with how submicron IR or O-PTIR works. And then follow up with a couple of examples showing how it actually works. All right. Okay, so then it goes back to the basics where we have, let's say, molecules, right? Then for us to identify what it is, we go back to using infrared, and that's because infrared spectroscopy gives us the functional groups and the connectivity between the atoms that SEM couldn't. So back in the college days, we learned how to interpret these spectrum, and that's because, well, based on these molecules, or the functional groups, we can figure out what the molecule is, and every molecule should have its own, unique fingerprint, IR fingerprint, and so that's why we can separate the difference between nylon versus polystyrene as a general example. And each of these will have, these functional groups that would have different vibrational movement. So then that's why we can then, based on these bands, we can tell what they are, right? All right, okay. So then, again, this is infrared. So then we are looking at very long waves. We're looking at 2.5 micron to 20 micron. And so then oftentimes when we have small particles like these, it just makes it challenging to get useful information out of it. And so then it's not the only reason, really. There's also the fact that a lot of times when we prepare the samples, they can be pretty rough on the surface. The surface scattering of the IR light actually would contribute to some of the distortion artifacts that we see. So for instance, we have pyramid. When it's made in a flat film like this, it's actually quite straightforward to get an IR spectrum that we can readily identify. But as soon as we change the form factor, going from a film to a sphere, like a 15 micron bead like this, it is not possible to accurately identify what this is, because now instead of having a single carbon band, now we have a doublet. And then as we shrink the particles further, we run into a derivative band shape where we have the scattering artifact. Now the peak actually shifts from 1731 down to 1707. So then you can tell me, like, if I plug this spectrum into the database, what am I going to get, right? Instead of ester, I'm going to get a ketone. So that's a misidentification right there. All right, okay, so then there are alternatives. For instance, we have Raman spectroscopy, and it does provide a very high spatial resolution, but it does, as a side effect, it does have this autofluorescence baseline that we commonly see, in particular for semiconductor and microelectronics packaging, because most of those materials do fluoresce very strongly. It is quite easy to get Raman spectrum when we have the material pure, but then as soon as it is contaminated with or having a color master batch of some sort, then the fluorescent baseline is going to be quite strong. Naturally, Raman is 8 orders less sensitive than IR, so then we oftentimes face a situation when we try to get more signal, then we burn the sample. Oftentimes that's what I see. A customer give a sample to me, I only see these holes on the surface. So then there is another workaround, and that is to shift the wavelength from 532 to 785, but we often trade it with time because it's less sensitive as the Raman shift has become less and less sensitive as we go to longer waves in the visible region. So this is how we get around it by using a different detection scheme. So this is how it works in the name of Optical Photothermal Infrared. And instead of just illuminating with IR light, we are introducing a secondary beam. It's the visible probe light. And this IR here is post-tunable, and we illuminate it to the surface, as shown here in the schematic. And we then detect the photothermal response as the material absorbs the IR, it heats up, and then it changes the refractive index on the surface. And this visible probe detects this change right here on the surface. And since now we're using a visible probe, we can achieve much higher spatial resolution than previously. And so then we can now get to a Raman-like spatial resolution, and we can easily resolve these sub-2 micron features. One added benefit is that even though, yes, we are doing this in a reflection mode, which a lot of people will know that reflection mode FTIR didn't really work, but for us, reflection mode actually does work. And we actually can get, using this detection scheme, we can get IR spectrum that we can directly match with commercial IR database. And we can do that despite the fact that the sample might have different geometry, irrespective of size and shape. So as I already mentioned, this is a non-contact technique, so we don't have to worry about cross-contamination. And oftentimes we can, a lot of the samples that we see, they are already prepared by existing sample preparation technique like CMP or FIB, so then you don't have to create anything new to make this technique work. And finally, there's no autofluorescence, so you don't have to worry about the quality of the baseline. And finally, this is how Mirage works. We're looking at the local photothermal response on the surface, and so that's why we have the name called Mirage. And this is the spatial resolution comparison. FTIR does vary in the mid-IR in terms of spot size, but for Mirage, it's constant. So that way we can keep everything constant. The contribution from each spectrum across the mid-IR will be equal across. So that actually helps us. Skip that. So in that sense, for FTIR, basically the reason why it's so difficult is because when we have very small samples, it's kind of like two persons talking in the in a concert hall. But whereas in the Mirage, we're actually listening to these small little changes, and that's why we can see these very high spatial resolution and high sensitivity measurement. For instance, we have a half a micron particle polystyrene, we can actually get a very nice IR signature that can match with existing database. And as an added benefit, we can also get simultaneous Raman and IR at the same time. So then this is why we have, and to answer that question, right, if we have a particle like this, can we actually analyze it? And yes, we can actually identify it with the O-PTIR, and then we can actually differentiate it from another particle that is on the same dye substrate. Now, I mentioned that we can use fluorescence, and that's what we can do. We can look at this stop edge here, and we notice that there is actually a backfill of this underfill from the underfilled resin material that is different than the solder mask. And so then, using this technique, we can using this fluorescence as a guide, we can quickly identify where the region of interest are, and then we can go straight to the analysis. And to a certain extent, it actually works really well enough that we don't have to go through IR imaging. We save significant amount of time doing this fluorescence imaging work. And so, as an example, we have contamination here on settling on the surface of the copper here. It blocks the solder from joining to it. Using fluorescence imaging, we can quickly identify where the region of interest may be. and we can clearly see that this area is fluorescing. And it does have a different color hue, so that actually tells us that it actually may have at least two different kinds of chemicals that is present. And this can be all done within less than 15 seconds, so that actually makes it really fast, a quick survey view. And finally, before to actually get to the actual identification of the material, then we point our laser beam, the two laser beam, right into that spot, and that will allow us to identify what this contamination is exactly. Based on these absorption bands, we know that it's proteins, and it is actually quite different than the underfill that we see on the side. Now we can then plug the data into the database, and we can figure out that these are, like, this is the this is a protein mixed with another material that is an acrylate emulsion. So by using a technique like the Mirage O-PTIR, we can identify contamination that is with a dimension of less than 2 microns. And this is not something we could have done in the past, and that's because of the lack of spatial resolution and sensitivity. But it's something now we can do with the submicron IR. And finally, I hope that I have shattered your common belief in the past 50 years or so that IR doesn't really work. It actually does. It's just that we have to change the way that we detect the IR signature. And we are able to achieve that with O-PTIR. And so then we now have excellent sensitivity, and we can combine with fluorescence FL-O-PTIR to achieve a quick identification. And finally, we don't have to worry about cross-contamination. And so at the end, we hope that this technique can help you identify what the the problem might be, and then hopefully we can then use this knowledge and improve yield. Thank you so much for the time, and if any question, I'll be more than happy to answer. And after this, I'll be probably in the back. You can trace me down there. All right. Thank you.
Okay, time for QA. We have a couple of minutes. Any question? So in terms of the element of detections or some molecular detections, so did we should we require to prepare for example micro joints through the cross section process first and then using your detectors?
It depends on the sample geometry that you're looking at. If you are looking at, let's say, a package microelectronics, like after the fact, then certainly the cross section would be better. But then once we backtrack to what the the source of the contamination is, let's say indicate what you see in the on the surface of the metals or the gold pad, then we can then do a top down. That's okay. Yeah, that's okay in that case.
So in terms
it's pretty flexible.
In terms of spatial resolution, is that possible to make a measurement for the micro crack resulting from some contamination?
Well, if the crack is air, then of course there's no IR signature we can generate from the opening. But if there are actually material hanging on the side wall that led to the formation of the crack, then or let's say if there's a difference in the these TGVs, right? Maybe there's actually on the side wall there's a slightly different stress on the silicon dioxide, then the infrared spectroscopy is going to tell us what is the strain on that silicon oxide by looking at the position of the silicon oxide bond on the IR spectrum. So we can do all that. But it depends on what is the subject of interest here.
So how about its spatial resolution?
Spatial resolution, we're looking at submicron on the lateral.
Any further questions? That's quite interesting results.
Yeah, it's a change of pace. That's useful. Okay. Thank you so much.
If not, let's assess and speak again.